Thank you. Good morning, everyone. I'm going to talk about a couple of natural language dialogue systems. One will be a machine learning system, and one will be a human learning system. And it's going to be more of a practical than a theoretical discussion this morning. But our application for using dialogue systems is to create virtual patients. Our virtual patients are avatar representations of human patients that our students can use to practice their history-taking skills. They're conversational. You can talk to the patients, they can talk to you, and generally they understand what you're asking them. And we have a variety of different sort of platforms for the virtual patients and uses of the virtual patients. We have a web-based, which is a chatted or typed conversation, and that's important when we talk about how you design a dialogue system to manage that type of conversation. We have a life-size version in the Clinical Skills Center that's a spoken conversation, and when we developed that, we were using Dragon Naturally Speaking. This was several years ago before cloud-based speech-to-text was available. And now our primary application is as an iPad version. We push the iPad app to our students, and it's a spoken conversation. We use cloud-based Watson for dialogue, for speech-to-text. And we currently also have a virtual reality version. You put the headset on, you're virtually in the room with the patient and conducting the encounter with the patient that way. So when you're designing a natural language system, there are some things you need to think about. You need to think about what's your input types are spoken. How are you going to understand the questions? Are you going to use a rule-based or a machine learning system? And then a little bit of what your output is going to be. That's important for our conversation, and our system may not be important for yours, but it is a consideration in terms of what you want your system to respond, how you want your system to respond. So input type, if you're using a chatted or typed conversation, those are kind of unique in the sense that the questions tend to be very succinct. People tend not to type really long, elaborate questions, at least our students don't. Their conversations are shorter, but spelling errors are something that you have to take into account if you're going to use that type of a system. There are autocorrect options available that help. That'll take care of many of the more common ones, but if you are in our domain, we have some pretty specialized words, and if the students or the healthcare providers misspell those words, it can make the dialogue system, can present challenges to the dialogue system. If it's a spoken conversation, it's quite a bit different. The questions are a lot longer, the conversations are a lot longer. You don't need to worry about spelling errors because your speech-to-text system is not going to send you back misspelled words, but it is going to send you back a lot of incorrect words. It's going to misunderstand what you say. And here's an example. This is an actual example from our application. So I'd be probing seems to help. So that's good. And so you you said this began about 4 to 5 years ago. You had another episode. Well, A, that's not even a question, so I'm not sure what we do with that. And B, I'd be probing is supposed to be ibuprofen. But Watson, when it was trying to understand that, made that I'd be probing. And so depending upon the type of the dialogue that you're working with, speech-to-text can introduce some pretty amusing errors. And then if you're doing a spoken dialogue, students will tend to lump several questions together. You're generally happy with your life now, your house, your job. Well, which one of those? The difference in our conversations than the typical application like Siri and Alexa, they can understand a wide variety of inputs, but you can't have a conversation with them. They basically understand one thing at a time, and you can't have a nuanced conversation. We're trying to do something completely different. Our domain is very narrow, but the conversations are very deep. So the first approach is not a machine learning approach, it's a human learning approach. Pretty much I'm the human who learned how to do this. It's a rule-based or pattern matching, sometimes called a handcrafted approach. Basically, our domain is narrow, so we're only talking about the questions that a doctor asks a patient. So we focus on those. That's a limited domain. Basically, use a software program that matches patterns. So I wrote actually probably now about 6,000 rules to manage that conversation. using the specifics of the software program. The software program does some things. It does canonization and parts of speech tagging and all of that. One of the most important things it does, though, is pronoun resolution and keep track of where you are in the conversation. In our domain, we have to know exactly what you're talking about. When a student says, "When did that happen?" we have to resolve that pronoun, and we have to know, are you talking about when did you take a medication? When did you hurt your back? When did you previously see the doctor? All of that is more difficult to manage, and you really can't ask Alexa or Siri, when did that happen? Because pronoun resolution is generally not a feature for that. And our accuracy rate with just a rule-based approach generally tends to be about 70 to 80%, depending upon a variety of factors. Depending upon whether the input is typed, we do better when it's typed than it's spoken, how complex the case is, whether it's a difficult history or a simple history. And one of the most important things is your audience. First-year students ask a lot of crazy questions, and so trying to manage those crazy questions compared to a third or fourth-year student that is going to ask focused questions that are easier to manage. So one of the things we wanted to do early on was to see if we could improve our dialogue system with a natural language, a more contemporary machine learning approach. And all of the work with the machine learning and the CNN approach is done with my colleagues at the Departments of Computer Science and Engineering and Linguistics, Dr. Mike White, Eric Foster-Lucier, William Schuler are the primary faculty members, and then we have a variety of graduate students who've worked on this, David King, Evan Jaffe, Liefeng Jin, and primarily the graduate student Adam Stiff did most of the engineering and programming for this system. So when we trained the CNN, we used a word and character-based CNN to identify the questions. Basically, the CNN almost always does worse than ChatScript. I've been writing patterns a long time. I know what the questions are. We're pretty good at that. And the CNN doesn't really have, in our domain, very many questions. There's not a big data set. Machines are good at learning, but they're pretty dumb. They need a lot of data to train the machine. And so for a number of years, the CNN was always worse than the handcrafted approach. But when we looked at the types of questions that were being missed, we saw that they were different. The CNN was better at some types, pattern matching was better at some types, and when we had a human retrospectively go back and classify those, we could get a dramatic increase in accuracy. So then we created a classifier, a binary classifier, to choose based on the types of questions that each one got right. And it was not as good as the human, but still gave us a pretty big increase in accuracy. And so we wanted to see, this was all done on retrospective data, could we create a live system that would do all of that in real time? And this was largely developed, again, by Adam. So last fall, we had all of our students interview Mr. Carlos Martinez. We had about 200 students, asked about 12,000 questions. And the first thing I'll draw your attention to is how well the speech-to-text did. This was delivered on an iPad. The students were doing this at home, watching TV. They were doing it at Starbucks, wherever, so not a controlled environment. Watson didn't do too bad, got about 70% of the input questions almost exact. Got about 90% acceptable. A human could understand what Watson was saying. And it just munged 10% completely and would just provided gibberish. In general, the results were the same. Overall, our accuracy was lower. These are now spoken conversations and not typed conversations. But in general, ChatScript gets about 70 to 78% correct. The CNN, always a little bit lower. The chooser, when it chooses between the two, again gives us an increase. We didn't get quite as dramatic an improvement on the live system. And there are some things that we did wrong when we were developing that, and we're going back and working on that. But one of the things we're focusing on now is the speech-to-text side of things. So Watson got it right in this situation about 70% of the time. But when we've looked at other systems, Watson is really untrained, not that good. Microsoft is about the worst. The word error rate for our domain anyways is about the worst. Google is about the best. Google's a little more difficult for us to to integrate into the system, so that's why we focused a little bit on Watson. Untrained Watson, about the same, but you can train Watson using a couple of different models based on your data set to make it better in your domain. And in fact, when we train Watson using our data, we can get it to be almost as good as Google and some of the others. So what we're going to do now is go back and use the train speech-to-text system to see if that improves our accuracy. We're using our new data to train the CNN. The more data you have, the better the analyzer. And so that's kind of where we're going in the future. The last thing I'll just talk briefly about is your output. What are you going to do? How are you going to have your system talk to you? Typically, most everyone will use a text-to-speech. Siri and Alexa, those are $1 million voices, probably $10 million voices. They sound like they do. Most people are not going to have access to those really high-quality voices. And you're limited also in terms of how your system responds. We needed some specific applications. We needed voices that had a specific accent, and we needed voices that had a lot more inflection. So we decided to actually pre-record all of our answers. That's very time-consuming, but you get a very realistic voice, and it can help you with specific applications that you got. So in summary, using a variety of different natural language systems, machine learning systems, human learning systems, our virtual patients, pretty good at answering questions. One thing I didn't talk about, they also categorize and classify all the dialogues and give immediate feedback to the students, and they can actually grade the encounter as well as a human can grade the encounter. Dialogue systems can be fairly simple, rule-based pattern matching approaches or sophisticated machine learning. The rule-based systems require handcrafting rules, but they're good to start with, especially if you don't have a lot of training data. Machine learning systems can be actually much more robust, but they require a lot of training data. And actually, hybrid systems can actually work pretty well. The 4 finalists for the Alexa Prize last year to create a conversational AI all used a hybrid system for their approach to manage the dialogue. And then depending upon the application, there are a bunch of variety of modern cloud-based systems. If you're just trying to create a simple Q&A sort of system, some of those might actually be a little bit better. And that's our support, and I'll turn it over to next speaker.